Then I'll open up the share screen to the book, and y'all can see that. Is that right? Can you see the book?
Yes, sir.
Okay. And recorder's going. So let me just do some housekeeping here, moving things around so I can see the screen better, because I've got toolbars that they just place them right in the middle of the screen, and it makes it hard for me to see the screen. Okay, I think I'll move the three of you up here. Okay, that will be better. And I'll scoot you over as far as, no. Okay. All right. Now that we're recording, let me go back in and kind of answer Melissa's question for everybody to hear. This weekend, I didn't have a lot of time to do much because we were out of town, and where we were had terrible to no internet service. So I couldn't, and I didn't have a printer there anyway, but I couldn't go back and find your print off any of your things. So yesterday we got back late Sunday. So yesterday when I had time, I printed off things, and I had hoped I got just about everything printed so I could get back to grading and then put grades in Blackboard. But I obviously didn't get far enough back because Melissa just had me find hers this morning. I didn't make it far enough back to find all the tests. So here's what else is going on. Now, before, see, I want to make this announcement, but I want to wait until more students are here, so I'll hold off that. But here's what, I don't know if you've seen this. Now, Melissa and Billy, you're both transient students, right?
Yes, sir.
Yes, sir.
Right. Dawson, you're not coming back in the fall. This is your graduating term, right? Dawson, you there? Okay. He may have lost Mike. Dawson, you are, okay. I don't have you muted, but I'll unmute you if I can. Oh, I just asked you to unmute. Okay. I can't hear you, Dawson. Can you hear me? Okay. I'm pretty sure Dawson's graduating this term, so none of you will be, yeah, right? Is that correct?
Yeah, I applied for graduation.
Right. So, this next thing I'm going to say really doesn't have that much direct effect on any of the three of you. I can't remember if anyone else in the class, I think the other three students are all transient students as well. So, so this doesn't pertain to any of you, but this is the big advising week that we have for fall term. So we've been asked to have expanded advising hours this week. I could only add one more hour to the 5 I'm already advising, so I'm up to 6 for this week. But, knock on wood, so far no students have signed up, even though it's the big advising week. They probably have signed up with other advisors, but I may be tied up with advising. That's why I was saying what I'm saying now. So I don't know how much time I'll have for grading. Since no one signed up for the 2 hours today, I don't think they can sign up inside a 24-hour limit. So I probably will have the 2 hours that I would be advising today to be trying to catch up on grading. But the dean has sent out, I think all weekend, all she did was send out emails. And I've been trying to make my way through the emails both yesterday and when I was trying to print out things, I was having to respond to her emails. And then this morning, there were more. So anyway, if I can ever get through all them, then I will try to find the rest of the tests like I found Melissa's and try to get those printed and then graded and then put on Blackboard. Now, the other part of your question, Melissa, was was something about going over the test or getting them back, or what was the issue there? I didn't quite follow it.
It said I figured you hadn't graded them yet because
Right.
not everybody turned them in.
Right.
And so I didn't know if that was the reason, because I have teachers who don't want to put in grades until everybody turned their grades in.
No, I usually, when I get them graded, get caught up on grading, I put in grades whether everybody's finished or not. It's just that I haven't gotten caught up on grading yet. And then once I get caught up on grading, then I'll put them in. But right now, I'm still in the printing mode because so many things have come in other classes recently. And I know this sounds like an excuse, and that's probably mostly what it is. We are transitioning from one management package to another. We've been on an ancient package called Alliant ever since we merged with Lawson. I was at Bessemer State Technical College. Back in 2005, we've been on this ancient, terrible old system named Alliant. The Montgomery, the two-year college system headquarters, has dictated that everybody has to go use the same system, and it's called Banner. And I don't know if y'all are familiar with Banner. I'm not very familiar with it, but that's what we're doing this summer, is transitioning to that. So much of my office hours for the last 2 or 3 weeks have been spent trying to get the Banner stuff done. And that's left me very, very little time for printing, grading, and entering grades on Blackboard. I'm hoping now that we're into the Banner thing, we're going to stop some of the ridiculousness that we were having to go through and let us just function, get back to doing what we need to do. So I'm working at, and I hope this afternoon, to get just about everything printed that's out there. And then once I get it printed, then I did get grading done this weekend when I didn't have internet service, but I didn't have a lot of time for that. But I obviously didn't get yours graded because I didn't have it printed yet. But I still I'm behind on getting it on Blackboard. But as soon as I get everything printed and then get everything graded, then I'll put everything I've got so far on Blackboard. So that is a terribly long and insufficient answer to your question, but I will get to it as soon as I can. Sorry that it's not done already. All right, any other questions, issues, concerns? Now, since it does seem like maybe I've got everybody here that's going to come in today, let me go on and make this announcement so I don't forget to. I'm hoping, I don't have any way to tell, that all 3 of you, and I hope all 6 of you, have completed payment. Because this came out from the Vice President. It was dated July 1st, but I didn't get it until the next day, I believe it was. And what he's saying here is you should not allow, let's see, if any regular term that's May through August, or mini term, June through August, this is only regular term, students in your class who are not on the official roll, meaning they have not completed payment, then they need to check with the business office, and there's a phone number here, or financial services office. I have a phone number for them too, to check on your financial obligations. Now, I don't want you answering out loud in case it's embarrassing or anything, but if you are not certain that your payment has gone through, that you are waiting on something, letters from your school, anything else, if you're not certain, then I would say, is there any way you can check and see on any of your documentation whether you're completed payment or not? I don't see the student side of things. So
I think if you go to your Lawson State portal, there is a section that said like remaining balance.
Okay.
And so it should see how much. I'm not sure how up to date it is.
Right.
But.
Okay. So you see, I guess I could go in the student suite, but I'm not a student, so I couldn't see anything that necessarily you could see. So yeah, if you'll go there and check and see if you have a balance, If you do, please contact either the business office or financial aid office to check on your obligations. He's telling us this. He says, call roll from your official class rolls. Well, guess what? I do the roll by whoever shows up in class, and I put them down. Now, I send out the invite to everybody that's on Blackboard. Now, if he wanted to do it right, he would just remove the names of unpaid students from Blackboard. Then they wouldn't get an invite, and then they couldn't get to class, okay? But he's asking us to do this and says, you should not allow the students to participate in class after tomorrow, Wednesday, July 8th. Well, guess what? If I send out the invite to everybody and you come into class, I guess I could not allow you in, but I'm not going to do that. Here's how I do things, and I guess this could get me fired, but you see, I'm ready to retire anyway, so I don't think they're going to fire me. But if you haven't finished completed payment, you're not on the official roll. And at the end of the term, only people on the official roll can get a grade. So I don't know why they do all this stuff. They either need to get them off Blackboard so they couldn't get to class, or they should just, if you sit in class and do all the work and everything else and you don't pay, you're not going to get a grade because you can't get a grade unless you pay. Okay? So that would be the simplest way to handle this rather than all this other mess that they do. They leave people on the roll forever, and then they ask us to not let them in class. Anyway, that's my little soapbox. I'll get off of it now. Are there any other questions or concerns or issues? All right, let's get started where we left off last time. We're in Chapter 4, Higher Order Differential Equations, in Section 4.1.3. Okay, I'm not sure I got all, no, 4.1.2 I think it is, even though this thing says we're in point 3. No, we're in point 2. So evidently the sidebar, oh no, I see. I went backwards from 3, sorry. So we are in 4.1.2, and that is, the title of that section is Homogeneous Equations, okay? And we were dealing with that before, and we moved from just talking about homogeneous equations to linearly independent sets or dependent sets of functions. That's where we left off last time. So a set of n functions, f1, f2, f3, all the way up to f sub n, so you have n functions, is linearly dependent on some interval I if at least one of those functions can be expressed as a linear combination of the rest of the functions, okay? So here they give you 3 functions. They're saying it, 3 functions, f1, f2, and f3. They're linearly dependent on that interval I if at least one of those functions is a linear combination of the other 2. Let's just say f3 is some combination, linear combination of f1 and f2. Now, you run into this concept a lot, not just in differential equations, certainly in linear algebra, but in all sorts of places. What we mean by linear combination, there's 2 big rules for lots of things, continuity, just all sorts of things. And that's if a set of functions is closed under addition and under scalar multiplication. Those are 2 big key issues. Closed under addition and scalar multiplication. And this concept of linear dependence is basically a combination of those 2. You see, we've added the functions, but not just the functions, but scalar multiples of the function. So if you could come up with some C1 and C2 that when you add them together, C1 times F1 plus C2 times F2, you can come up with F3. That means F3 depends on the other 2. That's where you get the concept linear dependence, because F3 depends on the other 2. And that has to be true for all the x's in I. that there at least one of the functions is a linear combination of the other two for all the x's in I, in the interval I. A set of n functions is linearly independent if no one function is a linear combination of the other functions. And certainly you can't try all the possible constants you got there, but there are ways to determine. So we move down to example 6. So I guess I ought to go to the white page here. So let's go to share on the white page. And let's do what they ask us to do here. I've got my board and I'm getting my stylus. Okay, now I've still got some housekeeping to do here because this toolbar is now in the way here too. Okay, I've gotten that out of the way. Now let's see if I can drag the whiteboard so I can get the most available white space. Yeah, that's probably as good as I can do. Okay, so here's example 6. The set of functions, I'm trying to get the pen to, my Wacom is not responding. Now this is strange. No, it isn't strange. I took my computer with me this weekend, and I just realized I didn't have my microphone hooked up. So I'm surprised. Okay. Okay. Can you hear me any differently now than you could earlier? Okay, sorry about that. I didn't realize I hadn't plugged in the microphone, and that also controls the Wacom. So, wow, if I hadn't done this, who knows when I would have realized it. Okay, so here's F1. F1 of x. Okay, this is it's a strange feeling to be writing in your lap. And F1 of x is equal to square root of x plus 5. The plus 5 is outside the square root of x. F2, and it might seem stupid to you that I'm heading downward here, but it's because I've got this block of your names and my picture right in the way here. The square root of x plus 5x, and the 5x is outside the square root sign. Okay. And F3 of x is x minus 1. Okay. Oh, here's a fourth one. F4 of x is equal, that's a terrible equal sign, x squared. I'm glad it was short because I was running out of room. Okay. Now, this is the interval that we're dealing with. I is equal to, anyone want to hazard a guess of what I could or should be here? Now, I see no reason that it wouldn't be including 0, but it does not include 0, okay? They have the I going only from 0 to positive infinity. Now, I don't know why that came up. Oh, okay. I equal 0 to infinity. Okay. Now, I can see why you don't have any negative numbers there. Square root of x, square root of x, can't have a square root of a negative number. You could have the square root of 0. So I don't know why they excluded 0, but it's okay. There's no problem with that. But this is the interval. And they say that this is a dependent set. And they just give you the answer without telling you how you got it, okay? Now, maybe I'm jumping the gun on what they're wanting to do, but let's go about seeing how they got this solution. Let's see if we can think through it first, okay? And I'll tell you the way I do it, but I have a lot more experience at it than you do. Since this F4 is the only term in here with an x squared in it, there's no way it could be dependent on the other three because none of them have an x squared, okay? And similarly, I don't see how F3 could be dependent on the others because that's the only one with an x by itself. Well, I'll take that back. Here you have a 5x. Okay, and here you have a constant here. So those three, there could be some way that the three of them are connected. There's no way F4 could be made out of a linear combination of the other three. So let's see if we can do that, okay? And let's see if we'll just come up with a C1 times F1. Now, to avoid a lot of writing, I'm going to write it this way. C1 times the square root of x plus C1 times 5. I'm going to write that as 5C1. Okay. Plus C2 times the square root of x plus 5C2x plus C3 times x minus C3. Okay? Now, if we can make that equal to 0, that means those three are linearly dependent. We know the F4 is not, so I didn't even bother to write that down. You could include that, but we don't need to. Okay? Now, if you notice this, there are two terms here with square roots in them. Okay? And those are the only two terms with square roots. There aren't any square roots on the right-hand side. So obviously, C1, if that's going to be true, C1 plus C2, yuck, that's supposed to be a C2. Let me come up here and see if I can find my eraser. Okay, make that look a little bit better. Okay, plus C2 has to be equal to 0. Okay, I should have spaced that out further. And here's why. Here we have two constant terms. 5C1 plus or minus C3. So 5C1 minus C3, that has to be equal to 0. Okay? And then we have two terms with x in them. 5C2 plus C3. That's got to equal to 0. Okay. Now, Dawson, I know, would want to do this as a matrix, and that would be perfectly legitimate. However, on first glance, just adding these two equations together would give us 5C2 1 plus 5C2 is equal to 0, and that you get from C1 equal, that basically says the same thing this is. So in other words, C1, and we could have written this down to it, has to equal minus C2. Okay? So we got that. So let's go down to one of these, and why not let's use this one. Instead of 5C1, I can't get it down here far enough, okay? We put in minus 5C2. This is getting us nowhere, okay? All right. Let's just go back and do it this way. Let's say that we have F2 minus F1. F2 minus F1. I'm not going to write down the x's there. And what that would be is the square root of x's will cancel out, and that gives you 5 minus 5x. Okay? Now, F3 is x minus 1, meaning and if you added that to this, if I can find my pen here, okay, so that gave you that. Let's also do this. F2 minus F1 plus 5 F3. Okay, well, these two added together we know is 5 minus 5x. Okay, plus 5x minus 5. That's 5 times F3. Obviously, that's equal to 0. Okay? Well, there we have a linear combination of these three functions that is equal to, I'm sorry. You have a combination of these three functions, and it is a linear combination of these three functions, added together giving you 0. So that means if you choose, and I'm just doing it this way, C1, this aggravates me, go to right, and it moves to select, okay? That minus C1 plus C2, I'm sorry, C1 F1 plus C2 F2 plus 5 F3 is equal to 0. There we've come up with a series of coefficients. C1 equal negative 1, C2 equal positive 1, C3 equal 5. Don't even bother with a C4. I mean, you'd have to have it equal to 0, okay? C4 equals 0 would be fine. But this linear combination adds to 0. That means, let's take C1 for instance, or F1 for instance, and have F1 of x. What I'm going to do is equal to C2 over C1. I'm skipping steps like crazy. F2 plus 5. Okay, I'm sorry. I've done this so stupidly. I wasn't thinking what I was doing here. Wait a minute. I don't need the C's down here. So if I can get the eraser to come up, pick up the eraser. All I wanted was a minus 1 there and a plus 1 there. Okay. and here too. Okay, sorry about that. Going crazy with my C's here. Here's a combination. Minus F1 plus F2 plus 5F3 equals 0. That means F1 is equal to F2 plus 5F3. There we have a linear combination of two of those to make the other. Therefore, this is a dependent set. Okay? The F4, it doesn't matter. It doesn't care what the others are doing. It's independent from the other three no matter what. But these three are dependent, one of them dependent on the other two. And you see, you could do any combination. You could do F2 is equal to F1 minus 5F3. Or you could do F3 is equal to 1/5 F1 minus 1/5 X2. So there's many ways to do that. They did it. They got it backwards from what I do. Did I make a sign mistake somewhere here? F2 is equal to F1 plus 5F3. I have F1 is equal to F2 plus 5F3. That wouldn't possibly be true. I must have made a sign error somewhere here. But anyway, you see what the deal is there. They depend on one another. One of those depends on the other two. F4 is independent of all of them. But F1, F2, and F3 are linearly dependent on one another for every X in that. We didn't have to enter an X in there. Every X, that would work. All right. Enough of that. And there's some little error there. I'm rubbing my finger on the screen when I should be using my stylus. So let's go up here and clear the drawings and go back to screen share if I can get it to come up. Go back to the text. Here we go. Well, there we go. All right. Now, that was dealing with linear dependence. Now let's talk about solution sets. Now, why this window keeps popping up here, fading in, fading out, I don't know. I moved my toolbar down here so it wouldn't be happening, and yet it's still happening. So it's just a stupid thing that Zoom is doing. I don't know why. Okay. Let me just make sure nobody's waiting to get in. Let me just check on that. Nope. I wondered if that had popped up and I couldn't see it. All right. We're primarily interested in linearly independent functions, or more to the point, linearly independent solutions of a linear differential equation. Because, you know, if you have arbitrary coefficients, you can have an infinite number of solutions. I mean, they just go on and on and on. But we want to know those solutions that are linearly independent from the others, okay, of a linear differential equation. Although we could always appeal to that earlier definition, turns out that the question of whether a set of n solutions, y1, y2, y3, up to y sub n, of a homogeneous linear nth order differential equation is linearly independent can be settled somewhat mechanically by using a determinant. Now, those who have had linear algebra, I know you know about determinants. Have the rest of you, have all of you had a run into determinants before? Yay or nay? You have. Okay, that was Billy. How about Melissa? Okay. As soon as this thing will get out of the way, we'll first run into, this thing called the Wronskian. And I'll mention where its name comes from. Joseph Maria Honnier, or something like Wronski, came up with this. And what this definition is, suppose that you have these functions, f1, f2, f3, all the way up to f sub n. So you have n functions, and that all these functions possess at least n minus 1 derivatives. Okay? You have n functions with at least n minus 1 derivatives, each one of them. Now, the Wronskian, called the W of those n functions, is listed as the determinant of, on the top row, we put the n functions down there. So you have n, you have one row with n functions in it, and we'll call those n columns. The next row, you put the first derivative of all those functions. The third row, you put the second derivatives of all those functions. The fourth row, you put the third derivative of all those functions. So the nth row, you put the n minus first derivative of each of those functions. So now you have an n by n matrix. N rows, your functions, and up to the n minus first derivative, that gives you n rows, and n columns, because that's how many functions you have. Okay? Now, the determinant. Okay? And by the way, for those who haven't, I'm trying to remember now who has turned in a research paper yet. I think just one of you have. So the other 5 you can fight over any of the other topics we've had so far, or now we have some more. 1, who in the world was Józef Maria Honne Wronski? I don't know if I'm pronouncing it anywhere close to right. A Polish philosopher and mathematician. Lived way back, that's about from the time of the birth of this country to almost the war between the states. Okay, so that's when he was alive and kicking, and he came up with this concept here. And let's talk briefly about what a determinant is, whether we're dealing with the Wronskian or not. Well, actually, it'll make more sense to do it. So if you hang on for just a moment with that request, we'll go over it sort of in gory detail. But let's scroll on down to see how we're going to use that determinant. Okay? Here's theorem 4.1.3. Criterion for linearly independent solutions. If you have these n solutions, y1, y2, y3, y4, y5, all the way up to y sub n, okay? N solutions for the homogeneous linear nth ordered, that's a length order, differential equation on some interval I. Now this is homogeneous again. Then the set of linearly independent, the set is linearly independent on I if and only if the Wronskian, which is a determinant, is not equal to 0 for every x in the interval. Okay? And hopefully, I know Dawson, if you've had linear algebra, you'll know, yeah, if you have a set of linearly dependent functions or other things like that, and you take a determinant of their coefficients, you have an n by n array. If one of them is dependent, if you come up with a, you're going to come up with a 0 determinant. Okay, that was way back there. All right, so let's scroll on down. It follows from this theorem that's right up there at the top that when y1, y2, y all the way up to y sub n are n solutions in the interval, the Wronskian W is either identically 0 or never 0. Okay, it's either 0 or it's not. That's all. It could be negative 753 thirds, or it could be positive pi halves. If it's not 0, then that's linearly independent. If it is 0, nope, linearly dependent. Thus, if we can show that the Wronskian is not equal to 0 for some x0 in I, then the solutions are linearly independent on I. Okay, now that seems like that's way too literal. Liberal, I guess, say of a definition. Let's see. For example, here are two functions. Y1 is cosine of 2 log x over x cubed. Oh, what a nice function that is. And y2 is sine of 2 log x over x cubed. Okay? And they claim they're both solutions for this differential equation. Okay? Y or x squared y double prime plus 7xy prime plus 13y is equal to 0. Okay? Now, just a couple of things here. Notice the interval here. I'm going to scroll down a little bit because I don't think we need the writing at the top anymore. Ah, here comes Ricky. Good to see Ricky's here. Okay. All right. Still missing the two C's, Corbin and Cole. Okay. Hopefully they'll be here. Now that I look at it, I think that maybe 5 out of the 6 of you anyway are paid. So I don't think if my little note on the side is correct, that by the way, Ricky, what I'm yakking now about is the fact that the vice president came out with a thing that after tomorrow we're not supposed to let anyone in the class again who is not paid. But if my notation is right in my grade book, I think all 4 of you and one other has paid. There may be one that has not, or it happened the last time I made the notation. So I forgot I put that notation in there. So anyway, y'all don't have to worry about, none of the 4 of you have to worry about payment. You are already all up to date as far as I can tell. Okay, now let's get back to this. Here we have 2 solutions, they claim, solutions to this differential equation. That's really a weird set of equations, these 2. Now, just the fact that we have an x squared as a coefficient for y double prime, that clues me in right there that x can't be 0. Because remember, this coefficient cannot be 0 anywhere on the domain. So therefore, I know why this has to start and not include 0. Okay. Now the question is, could it have been anything to the left of 0? No, it can't, because log x is in here. Logs can't be 0 and they can't be negative. Okay. So therefore, we have to be on the right-hand side of 0. Not counting 0, but any number to the right-hand side would certainly work. Okay. Especially when you write the answer like this. If you had chosen to write the answer cosine of log of x squared, then it would seem like you might be able to have a negative x, because when you square it, it's going to be positive. But they wrote it like this, and writing it like this, and that's probably the correct way to do it, that shows you, no, x's can never be negative and can never be 0, and certainly with x cubed in the denominator, it can't be 0. So we are in the right interval from 0 to positive infinity. Okay. Now, these 3 functions that you have here, x squared, 7x, and 13, the 3 coefficient functions, x squared, 7x, and 13, are all continuous on that interval from 0 to infinity, and a2 is not equal to 0. X squared cannot be 0. I already said that one. For every value in x, that's why you can't include 0 in there. Then you can start taking your derivatives. Now, I'm going to go back to the white page, whiteboard, I think it's called here. Yeah, the whiteboard. And let's do what they just did. Okay. Now, they haven't verified that this is a solution. It's okay. We can live without that. But here are our functions. Okay. be a little smarter this time and do y1 is equal to cosine of 2 log x over x squared, isn't it? No, x cubed. And y2 is equal to sine of 2 log x. It's almost reminiscent of that first test, isn't it? Over x cubed. Okay. Now, what we've got to do here, if we were verifying this, we would have already done it. Okay? But what we've got to do here is take the first derivatives. We only need the first derivative. Why? Because this is a second order differential equation. So you only need the functions and their first derivatives. So let's do those derivatives now. Okay? Here is y1 prime. Now this is going to take a little bit of effort here. As you can tell, we've got at least two different rules going on here. You got the quotient rule, which you could write as the product rule if you prefer to do that. And you also have the chain rule. Which do you prefer, quotient rule or product rule? Anyone have a preference? Okay, when I say product rule, here's what I mean. You could rewrite this as x to the minus 3 times the cosine of 2 log x. Write that as a product of two functions and then do the product rule, or as it written above, do the quotient rule. Which do you prefer, product rule or quotient rule? You tell me. Anybody? Product rule, I do too, okay? How does the product rule go? Okay, you said uv prime, so that would be x, if I can get my pen, come on down, there it goes, x to the minus 3 times, okay. Now, what's the derivative of this one? Start with the outermost function. What's the derivative of cosine? Anybody? Say again? Perfect, okay. Of 2 log x. But then you have the chain rule coming into play, and what do you multiply that by? Well, no, okay, no, you multiply the chain rule just by what the innermost is, derivative of the innermost part. And there, I would like to write that as log 2 of x squared. That would make it a little easier. That's the same thing, log of x squared. Okay, and you basically have two chain rules now. Okay, first the derivative of a log is 1 over, so that'd be 1 over x squared, if I could write, times 2x. Okay, this x is awfully ugly. Okay, so one of these x's goes out, and what you have left is 2 over x. Okay, now that's just the first part of the product rule. The second part is what? Plus anybody? Negative 3 times x to the minus 4. Derivative of the first times the second, which is cosine of 2 log x. Okay. Now, that's pretty ugly looking, right? Pretty ugly. That's okay. Let's see what this actually winds up being. This is 1 over x cubed. Here we have a 1 over x. So what we have here is a minus sine of 2 log x. Only you have a 2 in front. Yuck, it did it again. You have a 2 in front from right here. And that's over x to the 4th. And here we have a minus 3 cosine of 2 log x over x to the 4th. Okay, you see that? X. So, pretty interesting looking turn of events. Let's do our y2 prime. Goodness gracious, it's hard to write here. y2 prime is equal to, we do the same thing there, and let's write this first as a product. X to the minus 3 times a sine of 2 log x Okay. All right. Now, headset gets hot and itchy after a while. Okay. Okay. Now, if we do the chain rule on that one too, just like we did before, trying to get my pen back, there it is. Okay. That would be x to the minus 3, the first, times the derivative of the second. Derivative of the second now is a cosine of 2 log x. Now, we do the derivative of the inside. Well, the inside was the same as this one. So I can find it. There it is. It's 2 over x. Okay. I'm going to sort of shorten things a little bit, but that is 2 over x. Okay. Plus, only that's going to become a minus because this is going to be the derivative of the first, which is again minus 3x to the minus 4 times cosine 2 log x. No, sine, I'm sorry. I was looking at the wrong function. All right, let me find my eraser here. Okay. Oh, that's a problem. Okay. All right, let me, yeah. This is a sine here. It's a sine, okay. Sine of 2 log x. That x did not print very well. Okay. Okay, lots of parentheses there. Probably I don't need them all. Okay. So what does this give us? This gives us a 2 cosine of 2 log x over x to the 4th minus 3 sine. can't get the sign to right. Okay, of 2 log x over x to the fourth. Okay. I'm going to take a quick pause here for a moment. I'll tell you why in just a bit. I'm going to take off my headset. All right, sorry. I'm so loud and obnoxious that most of the time my wife's working at home too, and I have to keep the door closed because I'm so loud. And I'm upstairs in a bedroom, she's downstairs in the office, and still she can hear me. She has acute hearing, I don't. And so I have to keep the door closed. Well, she had to go into work this morning, and she was still here when I started class, so I had the door closed. And I realized it's getting stuffy in here. I think she's gone, and she was, so that's why I checked the window. And she's gone. So here's what we've got. Now, here we have our y1. Where is it? There it is. There's y1. Here's y2. Here's y prime, y1 prime, and y2 prime. Okay. Now what we're going to do is set up the Wronskian for those. So this is a terrible example to do it, but this will be what the example that Melissa was asking for, I think it was, of a determinant. And this is one of the most awkward determinants you'll probably ever take, but let's do it. So I'm going to clear this. So the Wronskian here of that set of functions and derivatives would be this. Okay. That was my bad. That wasn't the. I'm just going to clear the drawing. Okay. Now let's get started again. Here is the Wronskian of these two functions. Okay. And thank goodness they're just going to call them y1 and y2. They put the of x's in there. I'd even shorten that. Now, the Wronskian is a determinant. And that's what the solid, almost look like absolute value bars are, but they're enclosing a matrix, a square matrix, rather than a number. So they're not absolute value bars. Okay, and what goes on top here is the cosine of 2 log x. That's the function, okay, over x cubed. And this entry over here will be the sine of 2 log x over x cubed. And the first derivative of that we got before, and I'm real tempted to just pull out the minus sign here so I don't have to write it twice. And that would be a 2x squared. No, I did not put x squareds in there. I thought that's not right. And I don't know why they did. But I'm coming up here. If I can get my pen to move, get my eraser. Okay. Oh, erase it too also. Sorry about that. Okay. That would just be 2 times sine of 2 log x. It's an ugly n. Plus, I took the minus sign out, 3 times the cosine of 2 log x. Okay. and that's going to be divided by x to the fourth. Remember, we didn't do the x squareds on top and x 6 in the bottom. We factored them out, okay? Over here, it's going to be very similar. If I could get this to stop fiddling around here. They reversed the order and did 2, no they didn't, this is how we had it, 2 cosine of 2 log x minus 3 sine of 2 log x. Okay, and that was over x to the fourth. Now the book carried around extra things here. Okay, now what a mess. Okay, what a terrible mess. Now it says in the book, and this doesn't, oh, and what I left off here is my other bar here. I don't know if I can get it in or not. I'll try. There it is. Means, ooh, I didn't go up high enough. The determinant of that mess, okay? Now it says, rather than expanding this unwieldy determinant, we just choose a value for x. Now that doesn't seem fair, does it? Okay? And the value they choose for x is x equal 1. Okay? Now, this all goes back to a statement they said earlier, which I could not see they had justified. It says, and this is just above that Wronskian in the book, it says, note that the coefficient functions are continuous on the interval, and a of x2 is not 0 for every value of x. Okay, no, that's not it. No, it's above that, okay, right near the top of page 125. Thus, if we can show that the Wronskian is not equal to 0 for some x0 and I, then the solutions are linearly independent. And the reason for that is, for them to be dependent, they have to be dependent for all of them, all the x values. So, with that in mind, now remember our interval is from 0, but not counting 0, to positive infinity. Okay, so one of my favorite things to plug in would be 0. Would not do it. That's not even in the interval. But my next most favorite would be x equal 1. So let's try x equal 1. And let's see if it works there. Now, if it doesn't, that doesn't mean it doesn't work for any value. But if it works for x equal 1, then you found at least one place where it does work. And that's all you need is 1. Because otherwise, it has to be for all values. So let's do this determinant for, I'm going to write it in here where I've got more room, when x is equal to 1. When x equal 1, log is 0, right? Okay? And if log is 0, 2 times the 0 is 0. Cosine of 0 is 1 over 1 cubed. That would be a 1. If you come over here, though, and plug in x equal 1, log of 1 is 0, 2 times 0 is 0. Sine of 0 is 0. Okay? Down here, I'll put the minus sign out front, but this is again, this will give you a 0. Sine of 0 is 0, so that doesn't contribute anything. But this, when you put an x equal 1, that becomes a 0. Cosine of 0 is 1, so this gives you a 3 over 1. Okay? Come over here and plug in x equals 0 here. You get a 2, because this gives you a 0. Cosine of 0 is 1. That would be a 2 minus 3 times 0. When x equal 1, log of 1 is 0. 2 times 0 is 0. Sine of 0 is 0. So that doesn't, and this is 1. There's your determinant. All right. This one now is a much easier determinant to take. And here is the example of a Wronski, of a determinant that Melissa was asking for. But this is the simplest determinant you'll ever run into, and that's going to be, what you do with the determinant is do the down diagonal, which will give you, multiply those, you get a 2 minus the up diagonal, the product of the up diagonal, and that gives you a minus 0. The important thing, that gives you 2. These two functions are linearly independent because the Wronskian is not equal to 0. It's 2. Any value for the determinant other than 0 gives you independence. If it gives you 0, not independent. Now, 2 by 2s are the very easiest matrices to do. Since Melissa asked, I'll go on and do it. Let's clear the screen here and we'll do another one. Okay. Now that determinant we just did, I started to write on the screen, old habit. Okay. Let's do a 3 by 3. All right. 3 by 3 would be a 1, 0. Make up another number. Anybody? Give me a number. 4. Okay. And then I'll use the negative 3, 2 that we had before and make up another number. Any number. 1. Okay. All right. We need one more row here, so give me another number. Make up another number. 3. Another. 5. That's supposed to be a 5. And 6. Is that what you said? Oh, 2. Okay, I'm sorry. Doesn't matter. 2 will do it as well. Might be a little easier to work on. Okay. No guarantee. Okay, 2. All right. Now, if you have a 3 by 3 matrix, that's the next easiest matrix to deal with. Okay. Now, what you do with a 3 by 3 is, and this is a trick, but it always works. Repeat the first 2 columns. Oops. I don't know what I just did. Oh, there, it disappeared. Okay. Repeat the first 2 columns. 1, negative 3, 3, and 0, 2, 5. Okay, now I'm going to put the determinant bar here just to remind you that's what we're doing. You cannot take the determinant of a rectangular matrix. It has to be square. But we did this for a special reason. Again, we do the down diagonals. If I can get my pen to show up, there it is. Okay, do the down diagonals and multiply them together, and that gives you a 2 times 2 is 4. This one gives you a 0 because it has a 0 in it. This one gives you a negative 60. Okay, now I'm going to erase my construction lines there because they're just going to get in the way. So we'll erase that one, and that one, and do my up diagonals now. And remember, the up diagonals are always negative. Well, that's 3 times 4 is 12 times 2 is 24. So that's a minus 24 because it's the up diagonal. This one is a minus 5 because it's an up diagonal. And this one, of course, is a 0 because it has a 0 factor in it. Okay? Now, you don't have to do very much thinking to see that this thing is not equal to 0. If you're really wanting to know what the determinant is, you add those 3 negative numbers together and subtract. Well, I would subtract 4 from 5 and make it a negative 1 there, and then that would be a minus 85. Okay, that's not equal to 0, so therefore this Wronskian, if that was representing a Wronskian, that would be that set of functions, whatever that function was, who you wound up with that as a determinant, that would be linearly independent. Okay? Now, I hate to do this, but I almost have to just in order to satisfy Melissa's question. Okay. Let me show you. You do. Okay, there's no special rule. What you have to do is take a value. Well, okay, actually, you row reduce or column reduce now. It doesn't really matter if you're doing determinants. And try to get as many zeros in either a row or a column as you can. And then if you use that row or that column, then it's the value that's not zero. You wipe out its row and column and you have a 3 by 3 left, and you have that value times it. And you have the things of the cofactors and minors and all that kind of stuff. So you remember all that stuff now? Okay, all right. Thank you. We won't go any further. Okay, most of the time they're going to limit you to either 2 by 2s or 3 by 3s, just because they're really awkward past that. Okay, so let's go back to our, well, we can clear the screen. Let's go back to the screen sharing and go back to the text, which is moved over here now. I don't know why it moves around like this, but it does. Okay. Now, this is what we just did with that Wronskian. That's the Wronskian we came up with. Why they put the x squareds up here and x6 down here rather than to remove the x squareds here and put an x to the fourth here and here, I don't know. But then they just plugged in x equal 1, because for it to be linearly dependent, it must be true for every x. So if you can find one x that it's not, if we have found the x equal 1 produce a Wronskian of 0, then we'd have to try other numbers as well. And if we never could come up with another number, then we say, well, I guess it would have to be 0. Or then we'd go back and do actually the determinant of that mess of things and see if we can pan that out to be 0. That would have been a mess. But we just picked the fact that if there's at least one value for which it's not, then it's linearly independent. All right, now a new definition, which is a pretty important one, especially for later on. If you have a set, y1, y2, y3, all the way up to y sub n, of n linearly independent solutions, they have to be independent, of a homogeneous linear nth order differential equation on an interval I, it is said to be a fundamental set of solutions for the interval. Okay? Now, let's start with your differential equation. If it's nth order, that means you've got to come up with n linearly independent solutions before you have a fundamental set. You could come up with n solutions, but if they're not linearly independent, you don't have a fundamental set. You have to have the same number of solutions as you have order of your linear homogeneous differential equation. The basic question of whether a fundamental set of solutions exists for a linear equation, and they mean linear differential equation, is answered here. There does exist a fundamental set of solutions for the homogeneous linear nth order differential equation on some interval I. They just say it. They don't give you any proof or any rationale why they say it, but that's true. They're saying there does exist a fundamental set of solutions for the homogeneous, homogeneous linear nth order differential equation on the interval I. Excuse me just a moment. I'm getting very, very dry. Oh man. Now, analogous to the fact that any vector in 3 dimensions can be expressed as a linear combination of the linearly independent vectors I, j, and k, however you want to point them, any solution of an nth order homogeneous linear differential equation on the interval I can be expressed as a linear combination of n linearly independent solutions on I. In other words, n linearly independent solutions, which are the basic building blocks for the general solution. In other words, any fundamental set of solutions for that differential equation on that interval, any linear combination of them will be a solution. And that will cover basically all your possibilities if it's a homogeneous equation. So let's scroll down. Let me see what a page down will work here. Okay. Did that get us to, yeah, that gave us to the right place. Okay, scroll a little bit further. So here's another theorem. Let x1, x2, y1, y2, y3 up to y sub n be a fundamental set of solutions for the homogeneous linear nth order differential equation on subinterval I. Then what we call the general solution for that linear homogeneous differential equation on the interval is the general solution is y is equal to c1 y1 plus c2 y2 plus c2 3 y3 plus all the way up to c sub n y sub n of x, where the ci's I equal 1, 2, 3 up to n are arbitrary constants, not all of them being 0, because that would give you y is equal to 0, and that probably would be a solution. So even that would work, but that's just not very interesting. Okay, now that theorem states that if your capital Y of x, which I don't know where they got from, is a solution of your linear homogeneous differential equation on an interval, then the constants c1, c2, now they're capitalizing them, can always be found such that y1 of x, that solution you're looking for, is some linear combination of that fundamental set of solutions that you have. And it says we'll prove the case where n is equal to 2. Okay? And I don't know if you're interested in that proof, but let's just show it to you. Was there a question? Okay. So let's say y is a solution. Y1 and Y2 are linearly independent solutions of this differential equation, A2 y double prime plus A1 y prime plus A0 y equals 0 on some interval I. Suppose that x equal t is a point in the domain, in that interval, for which your Wronskian is not equal to 0. Okay? In other words, it is a value for which you have a non-zero determinant. Suppose that y of t is equal to k, and y prime of t is equal to y of t is equal to k1, y prime of t is equal to k2. Okay, at that one value, so it would just have one value. Now examine these equations. C1 y1 of t plus C2 y2 of t would have to equal k1 plus, you take the derivative of it, and that would be C1 y1 prime of t plus C2 y2 prime of t is equal to k2. Now, it follows that you can determine C1 and C2 uniquely, provided that the determinant does satisfy the condition that it's not 0. But that determinant is simply the Wronskian evaluated there. So in other words, this comes up with a system of equations, C1, C2, these things, and this goes back to Kramer's rule that if your the determinant of the coefficients. This is it's kind of a little backward feeling. Remember, t is a constant. It's just some value. So y1 is a constant there. y2 is a constant there. y1 prime is a constant there, and y2 prime is a constant there. We're looking for the unknown c1s and c2s. So things look a little backwards here. But to find out what they are, remember Kramer's rule. I don't know if you recall this. Your denominator would be the coefficients here. Now remember, the coefficients are what looking like functions here. The unknowns are your what looks like coefficients here. So the determinant of y1, y2, y1 prime, y2 prime right here is not equal to 0. That is from Kramer's rule, that guarantees that you have a solution, okay? Well, that thing's not equal to 0 because that's the Wronskian for this function. We already assumed that that is not 0 when x equal t. That's what they say right up here. Suppose that x equal t for which the Wronskian is not equal to 0. Well, this is the Wronskian, so you know it's not equal to 0. It feels like we're running around in a circle here, and that's what a lot of proofs seem to be. So if you define then they come up with a new name, g of x, which is some linear combination of those two, using those c1s and c2s that you supposedly just determined up here uniquely. We observe that G satisfies the differential equation since it's a superposition of two known solutions. G satisfies the initial condition, and G satisfies your initial condition of your derivatives, okay? And literally these proofs seem like they run you around in circles, so that's why I tend to ignore them as much as possible. What you want to know is what's true, and that's what the theorem tells you, okay? Let's do example 7 and actually see an example of that, which doesn't prove it, but at least it satisfies you and makes you feel like you're closer to a proof. Here are two functions, y1 and y2. y1 is e to the 3x, and y2 is e to the minus 3x. And they claim they're both solutions for the homogeneous linear, differential equation y double prime minus 9y is equal to 0 on the interval from minus infinity to positive infinity, because these e's are defined everywhere for all real number x's. Now, they say by inspection the solutions are linearly independent. And then I don't know why they say that, then they go on and prove it. So let's leave here and go to the whiteboard and do what they're saying to do. All right, we finish at 10:45, so don't let me run over. Okay, let me find where we are now. Yeah, example 7, bottom of page 126. So here's the first function. Get my tablet back here where I can write. Y sub 1 is equal to e to the 3x. This pen is doing strange things. Y sub 2 is equal to e to the minus 3x. Okay. Now, here's your differential equation, y double prime minus 9y is equal to 0. Now, this is much easier to verify, so let's go on and verify it. Because you need this first step anyway. Y prime, or Y1 prime, is equal to what? Yuck. 3 e to the 3x. Y2 prime is equal to minus 3 e to the minus 3x. Okay. Well, just for fun, we don't need it for our problem, but I'm going to do it. Y sub 1 double prime is equal to 9 e to the 3x. And y sub 2 double prime is equal to 9 e to the minus 3x. Now, the only reason I did that was to show that if you plugged y1 double prime in here, it'd be 9e to the 3x minus 9 times e to the 3x. That gives you obviously 0. If you plug this one in, y2 equal 9e to the minus 3x, and then minus 9 times e to the minus 3x, that gives you 0. So that's why I did that second line. It was real easy to show these are indeed solutions there. We're not interested in those second derivatives now. We want to know what the Wronskian is. And just for the practice of it, so the Wronskian here for these two functions, I'm not going to write them down, is the functions themselves, e to the 3x, e to the minus 3x, three e to the 3x minus 3 e to the 3x. Okay. Excuse me. Getting so I can hardly talk. So let's do our Wronskian here, okay? We'll do the down diagonal, and that gives us a minus 3 e to the 6x, and then do minus the up diagonal, which is a minus 3 e to the, no, I'm sorry. I left off a minus sign here, didn't I? So that gives you minus 3 minus 3, because e to the 3x times e to the minus 3x, that's the same as e to the 3x times 1 over e to the 3x is 1. And this gives you a negative 6, which is not equal to 0. So that guarantees that these are not just solutions. This guaranteed they were solutions, taking that second derivative and plug them in, but that they're linearly independent solutions. And since this is a second order differential equation, you have two independent solutions, you have a fundamental set. Okay, so what conclusion could you get from there? Your general solution, y, I'm not going to capitalize or anything, y of x, if I could get the pen to write, is equal to sum c1 e to the 3x plus sum c2 times e to the minus 3x. That is your, every solution you can have for that differential equation can be written in that form for some value of c1 and c2. Okay. So your general solution is y is equal to C1 e to the 3x plus C2 e to the minus 3x. All right, and that's what they get. I'll just go straight on here to go back to the text. And that's what they get. Y is equal to C1 e to the 3x, because they did their Wronskian just like we did. And when you do the cross here, that gives you a minus 3. But because it's up diagonal here, it's minus 3, which is minus 6. And that's not equal to 0. All right. That was so much fun. Let's go straight to another example. Okay. Now, here, oh, I don't like these. Well, we're going to get rid of them. Okay. The function y is equal to 4 times the hyperbolic sine of 3x. Now, this is not written in what I would consider the best form. If I were writing this, I would put that 3x in parentheses, and then the minus 5e to the minus 3x is outside the parentheses, so you don't think you're taking the hyperbolic sine of both of those. It's only the hyperbolic sine of 3x. And that says it's a solution for the differential equation in example 7. That was, the one we just did, okay? It says verify that. In view of theorem 415, we must be able to obtain that solution from the general solution that we got before, okay? Now, let's go back to the whiteboard and do what they say. I'll show you what I do with hyperbolic functions, okay? Oops. Probably not fair, but it's what I do. All right. Whoa, my goodness. Did I ever luck out here? I didn't erase this drawing. So let me erase everything except the answer. Okay, so I don't need this any longer, or that. Or this. This is almost as much fun as watching paint dry, isn't it? Maybe it would have been easier to just write down, erase it all and just write the solution down. Okay. I'm going to also erase that ugly X here and get my pen back. Okay. And then get back on my, put the X back in here. Okay, that looks a little better. All right, what they're saying now with example 8 is they're claiming that this is also a solution to that same set of equations. I did erase more than I intended. I'm sorry, let me go back and erase and write that back in again. The differential equation was y double prime minus 9 y is equal to 0, wasn't it? Yeah. And that's so ugly. I want to erase part of that. Minus 9y. Okay. There was our differential equation. Now, example 8 says this. Verify that y is equal to 4 times the hyperbolic sine of 3x, this is how I prefer to write that, minus 5 times e to the minus 3x is a solution of that differential equation. Now, before I do anything else with this, here's what I'm going to do. I'm going to write down what hyperbolic sine is, okay? Okay. Now, in case you don't memorize that, and I don't recommend that you do, please tell me it's in the book somewhere. Here it is, I think. No, these are Laplace transforms. Yuck. Okay. Yuck. All right. I'll just tell you what it is. This hyperbolic, can't figure out the best place to write here. Okay. The hyperbolic sine is e to the 3x minus e to the minus 3x over 2. Okay, now that's my memory. Let's see if, yeah, that's it. Okay, so that's what hyperbolic, and this is how I deal always with hyperbolics. Just go on and write down what they are. I'd much rather work with e functions than I would hyperbolic functions, because hyperbolic functions are so close in some of the properties to what sines and cosines are. You think you got it, but there's a sign difference, and if you don't remember the sign difference, you're in terrible shape. So this is equal to minus 5, equal to minus 3x. That was the rest of your function there. It was 4 times the hyperbolic sine, which is that, minus 5 times e to the minus 3x. Okay, well, obviously here, this 2 will go into that 4 twice. Okay, so what does this give us? This gives us 2e to the 3x. And here you have a minus 2e to the minus 3x, but there you have a minus 5, so that's a total of minus 7e to the minus 3x. Now, that's the thing they're saying, that's the function they're saying is also a solution to this. Let's see if they're telling the truth. Well, in the first place, yes, they are, because for any C1 and C2, we know this is the solution. Well, if you let C1 equal 2 and C2 equal negative 7, you got it. I think what they wanted us to do was take derivatives of it, which is not bad either. So let's do that. And the first derivative, and this is called y, so it's going to be y prime, is equal to 6e to the 3x plus 21 e to the minus 3x, and your y double prime is equal to 18 e to the 3x minus 63 e to the minus 3x. Okay. Whew. All right. Now, let's take that and plug it into our original function here. 18 e to the 3x minus 63 is a minus sign, e to the minus 3x I don't know why the pen sometimes only leaves a dot and sometimes actually writes. Minus 9 times 9 times 2 is 18 e to the 3x. Minus 9 times a minus 7 is a plus 63 e to the minus 3x. And sure enough, that adds to 0. So therefore, this is a solution. This 4 times hyperbolic sine, which is also this. And you see, that's exactly where C1 is equal to 2, C2 is equal to negative 7. Any constants that will work, we showed them. Okay. Now, example 9, a completely new set. So let's clear. My finger won't work on the pad. Here we go. Come on. There we go. Clear the drawings here, and let's move on to example 9. All right, excuse me just another minute. Oh. The one reason I'm so dry today, we were, my wife's family had a place at Smith Lake that we've sort of taken over when her parents wanted to build their retirement home, a single level, so they could get around more easily. So we were directed to buy it from them, and we did, and no problem. But we're now having to upkeep it, so we went up this weekend. It's out remote, isolated, in Winston County on Smith Lake. So went up, and of course have to work a lot there, yard and other mess. And I got eaten up by chiggers, and so the only way I can sleep at night is take Benadryl, and that knocks me out, so I don't notice the itch any longer. But it also dries me out like crazy because it's the antihistamine. So that's why everything is dry, and I'm having to drink fluids. Okay. So sorry. What's that? And what is that again? Uh-huh. Uh-huh. And, and it actually is nail polish or something else? Okay, thanks. I'll have my wife, she's very good at doing that. I know she got some stuff called, it's actually liquid Benadryl, and you put on it. It does stop the itching, but only for a number of minutes. It seems like not long enough for me to fall asleep, because right about the time I fall asleep, they start itching again. So I'll try that. You don't remember a brand name, do you? Right, right, right. Yeah, I don't like taking anything, and Benadryl just knocks me out. So that's why I'm dry today. All right, but thanks for that. All right, so here we have functions, okay? Let me get my pen turned over correctly. And here we have y1 is equal to e to the x, okay? y2 is equal to e to the 2x. y3 is equal to e to the 3x. Okay, They all satisfy the third order equation y triple prime minus 6y prime, y double prime, sorry, plus 11y prime minus 6y equals 0. Okay? Now, they claim that they do satisfy that. Not too hard to show. They don't ask us to, but we can. We're going to need these first two parts anyway, so let's do it. y1 prime is equal to e to the x, one of my favorite functions of all time. y2 prime, we're going to need that later anyway, and that's equal to 2 e to the 2x. Okay, y3 prime is equal to 3 e to the 3x. Why the pen does that, I don't know. We're going to need the second derivatives also, so y2 double, that's y1 double prime. Again is equal to e to the x. y2 double prime is equal to 4 e to the 2x. My nose is itching. y3 double prime is equal to 9 e to the 3x. Okay. Now, the next derivative I'm just going to call out to you. I think you'll know it already. And I'm just going to write it under here. Y triple prime, y1 triple prime is going to be e to the 3x, e to the x, minus 6 times 4 would be minus 24. I'm sorry, doing the wrong one. Y double prime, that's just going to be 6. I'm doing, y1 to begin with. Okay. Plugging in the y1 values here. y1 double prime is e to the x, so it's minus 6 e to the x, plus 11 y1 prime, which is e to the x, minus 6 times y, which is minus 6 e to the x, is equal to 0. Now, hopefully that'll go away. It does. Equals 0. Now, just want to point something out to you. E to the x is never, ever, ever equal to 0. It's strictly a positive function for forever. I mean, when x is very, very, very small, negatively, incredibly negative, it's approaching 0. When x is very large, it's approaching infinity. It never, ever crosses the x-axis. Okay, so it's never equal to 0. So that means the coefficients had better be summed to 0. Well, sure enough, they do. Minus 6 is minus 12, plus 1 and plus 11 is plus 12. That's equal to 0. Okay, and we could go back and plug each of those others in. The first one would have been an 8 e to the x for this one. Minus 6 times 4 is minus 24. That's what I was starting to do before. So let me just write down the coefficients for those. Okay, that would have been 8, because when you do y2 triple prime, that would be 8e to the 2x, minus 6 times 2 is minus 12. Minus 6 times 4 is 24. Hopefully, I know I'm skipping so many steps here. Minus 6 times e, so y double prime, I'm looking at the wrong thing. Here's y2 double prime is 4, so it's minus 6 times 4 is minus 24, plus 11 times 2 is 22, minus 6 times 1 is minus 6, okay? Again, add your positives together, 8 and 22 is 30, and add your negatives together, negative 24 minus 6, negative 30. That adds a 0. Let's do the big one there. When y3 triple prime would be 27 e to the 3x, so I'm just going to write down the 27 because they all have e to the 3x in them. Minus 6 times 9 is 54 e to the 3x. Plus 11 times 3 is 33 e to the 3x minus 6 times e to the 3x. Okay, let's add your positives together and you get 60. Add your negatives together, you get minus 60. That's equal to 0. So sure enough, all these solutions work. Okay, so let me erase that. They didn't say we had to verify, but that one was easy enough. I thought it was okay to do. So we have verified that all three of those solutions are solutions. Now, the next thing we have to determine is, are they linearly independent solutions? Okay. They satisfy, we verified that. Now we just see if they're linearly independent. Well, what we do is the Wronskian. I'm not going to write the functions in there, but the Wronskian for these three functions would be the determinant of the function e to the x, e to the 2x, and e to the 3x. This pen just is bizarre. The first derivatives is e to the x, e to the 2e to the 2x, and 3 e to the 3x. I don't know why it writes like this, okay? And the second derivatives are e to the x, 4e to the 2x, and 9e to the 3x. All right, now remember the trick for the 3x3s. I regret that I wrote that last little, come on. Okay, put that line in there. Okay. Okay. What I'm going to do is repeat my first column, e to the x, e to the x, e to the x. Repeat my second column. Okay. E to the 2x, 2e to the 2x, and 3 and 4e to the 2x. Now we write that vertical line in there. Okay, this is how you do 3 by 3s determinants. Let's do the main diagonal down. If I can find it, there it is. Okay, the coefficient's going to be 18. Your exponent is e to the x times e to the 2x is e to the 3x plus times e to the 3x is e to the 6x. Okay, do the next diagonal down, and if I'm nowhere close, there it is. It's e to the 2x, 3e to the 3x, e to the x. So that's just going to be plus 3, and e to the 2x, e to the 3x is e to the 5x times that is e to the 6x. Third diagonal down. That times that times that. That looks like a plus 4 times e to the 6x. Okay, if I can erase my doodle there, and this one too. All right, an important thing in doing determinants is to keep things in rows and columns neatly. I haven't. This pen is really hard to do that. Let's do our up diagonals. Basically, that's a minus 2. E to the 6x. This one will be a minus 12. E to the 6x. Okay, and this one will be a minus 9. E to the 6x. Okay, have I just lost a couple people? No, we're getting closer to the end of the class, but we're not there yet. It looked like but Billy and Dawson both disappeared. So maybe one of them had already left earlier. I don't know. Don't know. I think there may be rain in the area, so maybe people are having trouble with their connections. I don't know. I have a problem here. I've noticed it till now is that my cords are all tangled. See if I can untangle them a little bit. Okay, that's better. All right, let's see what our Wronskian is then. Let's add our positives together. That's the 7 plus 18 is 25 e to the 6x. And here we have 21 minus 2 is 23. That looks like it gives us 2e to the 6x. It really doesn't matter what it is. The key is it's not equal to 0. Let's see if that's the same. Yep, that's the same thing they got. 2e to the 6x. Okay, so what were we to do with this problem? Here's the functions. They satisfy the third order differential equations. We verified that. All three of them did. We looked at their functions, the derivative and their second derivatives in a matrix, and took a determinant of those, and we found out that's not equal to 0. For every real value of x, 2e to the 6x is never equal to 0. Okay, and we can conclude then that the linear combination of these three functions, and that would be written this way, y of x is equal to c1 e to the x plus c2 e to the 2x plus c3 e to the 3x is going to be a general solution for that differential equation for any value, C1, C2, and C3. Okay. Yes, that will definitely be the case. Okay. Because the Wronskian not being 0 showed that these three were independently, linearly independent of each other. And you had three of them, third degree linear differential equation. You know it's got to be, that will be your fundamental set, and any linear combination of fundamental set will define your solution. And there it is. All right. And where that left us here, let's go back to the book. If I could, let me just do this. It's easier to use my finger here. And what we just did was example 8 and then example 9. So we did conclude that y is equal to c1 e to the x plus c2 e to the 2x plus c3 e to the 3x is a general solution of that differential equation. So we're finally ready to move on to non-homogeneous differential equations. Okay. Now, I think you'll find they turn out being way easier than you might expect. Okay, well, at least the first part is anyway, because it's what we've already done. Now, how are we doing on time? We got 3 minutes. Let's see what we can do in 3 minutes. Any function y sub p free of arbitrary parameters that satisfies your differential equation that has non-homogeneous, it has a g to the x to the right-hand side, is said to be a particular solution of that equation. Not got an arbitrary coefficient, okay? It's a particular solution. For example, it is a straightforward task to show that the constant function y sub p is equal to 3 is a particular solution for the non-homogeneous equation y triple prime. Okay, now we may have time to do that first simple thing, but probably not, and give you homework exercises too. So let's just stop here and figure we'll start with that example right there. Not really an example, but illustration, you might say, of a very simple non-homogeneous differential equation. So let me get my paper in place, and let's go back to the homework exercises. We are really close to finishing 4.1. All right, from 4.1.1, any of the odds either 1 or 3. If those answers are in the back, try one of those, at least one of those. Either 5 or 7, if those answers are in the back, do at least one of those. Do number 9 if that answer's in the back. Do number 11 if that answer's in the back. Then 13 if its answer's in the back. Then 4.1.2, any of the odds 15 to 21, if those are in the back, try those. That's about where we started today. Okay, 23, any of the odds 23 to 29, if those answers are in the back, do at least one or more of those. And then the non-homogeneous 4.1.3 we'll get to next time. Hopefully we'll finish that fairly quickly and move on to 4.2. And after we finally finish 4.2, and it's fairly short, okay, then we'll finally get to solving these. Rather than them giving a solution for us to verify and then blah, 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 we'll actually learn how to solve them ourselves. And a lot of the ones we've just done, you'll see exactly where they came from, okay? So that's going to be the task from there. Any questions, any comments, any responses? Yes. Okay, I'll do my best to try to get the rest of the material that's been sent in to me printed today if I possibly can, and then get to grading that material, and then hopefully at some point be able to start putting it in Blackboard. So, yes. Whenever you finish it, that'll be perfectly fine. Yeah. So whenever you get that through, I'll be printing those off too. So yeah, thank you very much. No, anytime you can. Good question. Any others? All right, glad y'all stuck with it till the end. Let's go on. Ricky, by the way, how is your dad doing? Maybe Ricky doesn't hear me anymore. Okay. Anyway, we'll stop the sharing and stop the meeting. Any last thoughts, parting shots before we go? All right, you too. Thank you so much. Bye-bye.